The next topic is the hypotenuse leg theorem. If you have two right triangles, I can't stress the next statement enough. The hypotenuse leg theorem, also abbreviated HL theorem, is only valid for right triangles. If you have two right triangles and the hypotenuse are equal and one leg is equal, these two triangles are congruent. Because if I call this length A, well then that length is A. It's the same length. And I call this side B, well then this side is B. And we will call this X. Well, Pythagoras, he would jump on this one. He would say, if you take each leg and you square them, and then add them up, you will get the hypotenuse. X squared plus B squared is equal to A squared. But that's the same, but that's the same in both triangles. B squared, or X squared plus B squared is equal to A squared. So in both triangles, taking away B from both sides, that is B squared from both sides, X squared is A squared minus B squared. So X is the square root of A squared minus B squared. That is, all three sides are the same. They both have a side of B. They both have a side square root of A squared minus B squared. And they both have a side of A. And all we started with is the hypotenuses were equal, one leg were equal, and a right triangle. And then what we got is SSS. Side, side, side. Corresponds to side, 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 or is congruent to side, side, side. So if you can show that in a right triangle, you have two right triangles, if you can show the hypotenuse and a leg are equal, you're done. Now, I said that these two triangles, 1 and 2, are congruent by side, side, side. I could have also said side, angle, side. Side, angle, side. I could have said that as well. Now, while we are on this topic, I want to make the following statement as well. Doesn't even have to involve the right triangle. If two legs are equal in two right triangles, we have two right triangles. And if you come to know that these two are equal and those two are equal, you are done. You are done. These two triangles, 1 and 2, they are congruent because they have a side in common, they have a second side in common, and they have the angle in the middle congruent. These two triangles are congruent by SAS. So basically, if you have two right triangles and they have any two sides, if two sides in one are the same as in triangle 1 are the same as two sides in triangle 2, you're done, with one exception. You can say, well, this is 3, these are both 3, this is 4, and that's 4. No. You either have to use the hypotenuses Okay, let me be really clear. These two are legs and they are equal. And this is a hypotenuse and a leg and they're equal. That's not good. Those two triangles are not congruent. They're either you use the hypotenuse and a leg and the hypotenuse of a leg, or you use leg. And they must be right triangles. If you have the hypotenuse and the leg of one triangle, right triangle, and they match the hypotenuse and the leg of another right triangle, those two triangles are congruent. If you have two legs of one right triangle, and they're the same as two legs of another right triangle, these triangles are congruent. Okay. In other words, you can say HL is congruent to LL. That you can't do. That you can't do. And again, right triangles. Okay. And now that I confused you, let's try to work out a couple of these problems. Suppose we have two right triangles. We have a figure as such. Oops. Okay. These are right angles. A, B, C, and D. And let's see what we're going to be given. What do we need to be given? BC and AC are perpendicular, and BD and AD are perpendicular. That's what makes these right angles. Okay, so let's even not state it to start with. It's not part of the given. And we know we also are given that AC and AD are the same ones. And we want to prove that AB bisects line segment AB bisects angle CAD. Well, CAD is this big angle here. So if something bisects it, it cut it into two equal parts. And once I can show that angle 1 and angle 2 are equal, I am done. Well, I see a big triangle on top, and I see a big triangle on the bottom. The triangle on top is ABC, just the top half, everything. One triangle is above this line AB, and one triangle is below that angle. And I want to show that those two angles that I just erased are in fact equal to one another. I want to show that they're equal to one another. So, statement, reasons, and let's go through the logic. The first thing is just the given. Okay, so I am told that AC and AD are equal. I have a right angle, and the hypotenuse is always opposite the right angle. Well, they're equal. So in triangle 2, I have the hypotenuse and the leg, 1 slash and x slash. And in triangle 2, I have one leg with 1 slash and the hypotenuse with an x. That is, by HL is congruent to HL, those two triangles are in fact congruent. And then I'm going to argue that angle 1 and angle 2 are corresponding parts. Okay, so first I have to say that angle C is a right angle. Angle D is a right angle. Why? Perpendicular lines meet or meet at right angles. Okay. So now I will say that triangle ABC and triangle ABD are right triangles. A triangle with a right angle is called a right triangle. Okay, number 4. AB is congruent to AB. Reflexive property. Number 5. Triangle ABC is congruent to triangle ABD. ABD. And the reason is HL is congruent to HL. Maybe this should have been statement number 6, and statement number 5 should have been AB is the hypotenuse to triangles ABC and ABD. And why are they hypotenuse? The side opposite the right angle is called the hypotenuse. Alright, so before I can say H and L, I had to state that A side AB was in fact H. Alright, now statement number 7, which goes on top, please. I have the two triangles congruent, so now I'm going to say that angle 1 is equal to angle 2, and the reason is corresponding parts of congruent triangles are congruent. Now, oops, for some reason you can't read that, sorry. Statement 7, angle 1 is congruent to angle 2. The reason is corresponding parts of congruent triangles are in fact congruent. Okay, now why is that? Well, let's see. Angle 1 is made up of 1 slash and x slash. And angle 2 is made up of, what do you know, 1 slash and x slash. Right. I want to show that AB bisects CAD. Let me say that angle 1 plus angle 2 equals angle CAD. Equals angle CAD. And the reason is the sum of the parts equals the whole. The sum of the parts is the whole. The sum of the parts is the whole. Statements, reasons. Now number 9. AB bisects angle CAD. And what's the reason? AB cut angle CAD into 2 equal parts. Okay, and that's called an angle bisector. Long problem. For those of you who want to study math, it's very, very important that you get the hang of writing up these proofs. Because as a math major, and eventually mathematician, you're going to have to write up proofs all the time. Alright, how about we have this problem? You have the center of the circle being called O, and you have this triangle in there. You call this a E, F, and good old G. You are given the following. You are given that OF is an altitude to triangle EGO. Means it's the height. And you want to conclude or prove that EF and FG, EF and FG the same. Now, basically, if you have any chord, the altitude, and that's the center O, the altitude always meets at a right angle. That is, we have 2 right angles. And in fact, it cuts the chord in half. Cuts the chord in, well, actually, we don't even have to say that. We don't even have to say that. We know that these hypotenuses are the same. Why? Because they're each a radius. They go from the center to a point on the circle. That's one radius, and that's another radius. And, of course, OFs are equal to one another. OFs are equal to one another. So by hypotenuse, the check marks are the hypotenuse, the x's is the leg. By the HL theorem, we know that these 2 triangles are congruent. And then EF and FG are equal. That is, if you take any chord in a triangle, in a circle, and you go like this, and you go like that. Well, actually, you don't even have to go like this and like that. if you draw the altitude, that is, if you go dead center and you connect this line, well, I take that back because that defeats the whole theorem. Of course, it bisects it. If you draw the altitude, it turns out that this length and that length will be the same. They're the same length. So let's write this up. Statement, reasons. Try not to run out of space. One is the given, and number two. We can say that EF is congruent to EF, and that's reflexive property. Reflexive property. And then we can say that EO and GO are radii. And then we can say all line segments that go from the center of a circle to a point on the circle are radii. The plural or radius. Number 4. EO is congruent to GO. The reason is all radii of the same circle are congruent. Fine. Okay. So now, all we have is, let me just erase this. All we have is that in triangle 1 and triangle 2, two sides are equal in length. They're congruent. Now, if only we had a right triangle, we'd be in good shape. So, that's just what we're going to state now. And if I may, let me continue here. Angle EFO and angle GFO are right angles. And the reason is, see how we say this. In altitude of a circle, of a triangle forms right angle with the side to which it is drawn. Forms right angles with the sides to which it is drawn to. In other words, if you have any triangle, and you go to this point, to draw an altitude, by definition, you go to the side underneath it, but it better form a right angle. If you have that triangle and you want to form an altitude at this point, goes down in such a way where you meet at a right angle. Of course, both sides are right angles. Okay, so now we have that EFO and GFO are right angles. Now I want to say that the triangles 1 and 2 are right triangles. Triangle EFO and triangle GFO are right triangles. And the reason is a triangle with a right angle is a right triangle. And I know they have right angles. Look at statement number 5. Okay, now we can say number 7. We can now say, we can now say that triangle EFO and triangle GFO are in fact congruent. And the reason is the HL theorem. Remember, so now we have right angles. Opposite the right angles are the hypotenuses, and they're equal. And they have a leg that are equal, namely OF. Okay, run out of room, but now let me come here, please. Statement F is EF is congruent to FG. That's the statement. That's the statement. And the reason is congruent parts of congruent triangles are in fact congruent. Now, why are they corresponding parts? Well, they're the third side of a right triangle. They are in between. EF is in between the angle with no slashes and the right angle. FG is in between the side with no slashes and the right angle. So they are corresponding. Let's try one more. Suppose we have this along with their diagonals A, B, C, and D. And let me figure out what we are given. Say AB is perpendicular to AD. And we're also given that CD is perpendicular to AD as well. And their diagonals, they must be congruent. AC, BD. This is basically the definition of a rectangle. And we want to prove that we want to prove or conclude the following. We want to conclude that triangle BAD is in fact congruent to CDA. We want to prove this. Okay. So let's see what we are given. We're given that AD and AD are congruent. That means they meet at a right angle. CD and AD are perpendicular. If I said congruent, I meant perpendicular. AD and AD are perpendicular. CD and AD are perpendicular. And AC and BD are equal. Now that's kind of hard to draw because if I put a slash here, you may think that only BE and AE are congruent or equal in lengths. So let's not do that. But we'll understand the diagonals are equal. We'll understand the diagonals are in fact equal. We want to conclude that BAC, this top triangle, BAD, and CDA, this lower triangle, are congruent. They have the top left and the bottom right. You want to show that they are congruent. So AC, I'm looking right here, AC, so I'll call them triangle 1, triangle 2. AC is the hypotenuse of triangle 1, and AC is the hypotenuse of triangle 2. And they're equal. All right. Now, the one thing I didn't really use in this little story is BD is the same length. Okay. So now, all right. So, statement reasons. And somehow, I have to figure out how to get another side to be equal. So 1 is all a given. Statement 2 is AC is the hypotenuse to triangle 1, that is ADC. And while we're at it, AC, the hypotenuse to triangle 1, and to triangle 2. I left out something, I'm sorry. We're going to call this number 3. Number 2 will be angle ADC is a right angle, and angle BAC is a right angle. Perpendicular lines form right angles. And number 3, so now we have number 3, triangle ADC and triangle BAC are right triangles. Why? any triangle with a right angle is a right triangle. And now we come to 4. Now that we have a right triangle, now and only now can we mention hypotenuses. So of course 4 should really go in this 3. So this statement right here should go under statement 3. AC is a hypotenuse. Okay. The side opposite the right angle is called the hypotenuse by definition. Okay. And now we're up to statement number 5. For statement number 5, I am going to say that AC is equal to AC. And this is by reflexive property. So now I have the hypotenuses of 2 right triangles being equal. Oh. Do have your triangle 1. Am I doing this completely wrong? Triangle BAC. Okay. So this is fine. This is fine. So now in triangle 1 and triangle 2, I have the hypotenuse is equal. Basically, we're not really dealing with that yet. Oops, let me not hold the marker when I do that. So basically, we're not even dealing with that other side yet. Okay. All right. So now what I need to get is another side equal. Need to get another side equal. And how are we going to argue that another side is equal? Okay, so number 6. Triangle 1, sorry. ABCD is a right triangle. I didn't mean that either. ABCD is a rectangle. Any 4-sided figure with diagonals of equal length is a rectangle. Okay, number 7. AB equals CD. Length AB is congruent to CD. That is, AB and CD are equal in length. Opposite sides of a rectangle are equal. Okay, so now I am done. Number 8. I am now going to say that triangle BAC is congruent to triangle CDA. That's the statement. And the reason is going to be hypotenuse legs theorem. Well, in triangle 1 and triangle 2, the hypotenuses are equal. And in triangle 1, we have one leg equal to a leg in triangle 2. That's enough for me. Okay, there's the proof. And that completes this section.